Good morning, everybody. Hope you're all well. Okay, as Dan mentioned, my name is Andy Greaves. I am the East Coast Applications Engineer for Kyocera SGS Precision Tools. I cover 20 states from Maine down to Florida, as far west as Tennessee. I have been working for Kyocera SGS for about 5 years. I spent just over 4.5 years of that working for our Tech Hub division down in Danville, Virginia. There we offer engineering solutions for special tools, more unique applications than our standard catalog items. So we can work closely with the customer to develop a multi-tool that completes 2 or 3 tasks rather than using 2 or 3 different tools. And it also can, that facility can also be used for doing regrinds. During my 4.5 years there, I was also the on-site support engineer for Rolls-Royce Crosspoint, as well as our on-site engineer at a research facility called Zcarb, Commonwealth Centre for Advanced Manufacturing. There are industry members from across the country and globally that offer that come together to collaborate to basically everybody help themselves improve a matter of business. Before that, I spent 8 years working for a company called the AMRC in the UK, which is the Advanced Manufacturing Research Centre. And that's kind of where I cut my teeth. It was my first job out of university. And there I learned milling, turning, programming, 3 and 5 axis, predominantly on aerospace components made out of titanium, Inconel, and some aluminum products as well. Again, that was working closely with Rolls-Royce. I emigrated to the United States in 2017. I currently live in Richmond, Virginia. So let's get on to some more introductions, and we'll cover a bit of titanium and the history about it. Many of you probably know some of this already, but I just wanted to give a good bit of information as to the material and how it's used and the different types. So it was first discovered in England, 1791. It's predominantly used in the aerospace, military, medical fields. Because of its mechanical properties, its corrosion resistance, its low thermal conductivity, it makes it an ideal material for specific applications. Approximately two-thirds of all titanium produced is used for aircraft, which is pretty impressive. And there are 3 different types, phases of titanium, which we'll cover in a second, but there are many different groups within that as well. The composition of these materials can vary, producing different properties that are advantageous to specific applications. The first phase of titanium alloys is the alpha phase. This is pure titanium. It's pretty easy to machine in terms of titanium, but it does lack some of the good things that the alloy phases do give you. Excuse me. So these are generally respond well to heat treatment. They're very weldable, commonly used for airplane parts, as well as more temperature variation parts, so chemical processing, cryogenic applications really lend themselves to those niche areas of manufacturing. Second phase is the most common. This is the alpha beta phase. The most common titanium from all this is the one most people are probably familiar with. It's Ti 6Al4V. And this is a widely used material in the aerospace industry. It's great for engine components, airframe structures, landing gears, and it's also got great corrosion resistance. So it's also good for marine applications where you're encountering salt water often and other chemicals that would otherwise affect other materials negatively. Final phase is the beta phase. These are more tough versions of titanium. They have higher levels of molybdenum, vanadium in it, which does make them more difficult to machine. They are becoming more common because especially in aerospace, as engines are developed to run higher temperatures, higher pressures, that requirement for higher material properties is increasing constantly. And as mentioned in that bottom point, they're used for heavy duty purposes on aircraft as well. So, as I mentioned, there's a wide range of titanium materials out there, versions of material out there, and these are just 5 relatively common versions of the titanium there that you'll probably come across and have worked with in business. So, as mentioned, 6AL4V is the most common. It's used in aerospace, sports, marine applications. There are some automotive applications on this, but this is more your high performance, racing, exotic cars sort of applications. The Thai 6AL4V ELI is a more medical specific version of 6AL4V. This has better compatibility with the human body, so there's less chance of any issues of non-compatibility with the human immune system. And this can come from skull plates, brackets and pins for holding bones together, and joints as well. Thai 3AL2V is a heavier version of titanium. Again, this is a really specific material for applications where high heat, high chemical access is exposed often, and it lends itself to pressure vessels and heat exchangers, for example. Thai 5AL2SN is often used in airframe applications. It lends itself to these applications because of its resistance to creep and bend and fatigue. And finally, Thai 10V2FE3AL. This is for forged airframes. This is a really heavy duty titanium. It responds well to being forged and has excellent toughness. So it's great for these landing gear applications, especially in heavy duty, large scale aerospace. So think your Boeing A380 Max and your big military application aircraft, where we're moving lots of cargo around, and the planes are built to be that sort of scale. So moving into how you approach machining titanium. Now, machining titanium, as many of you know, it's not an easy thing to machine. There's many variables, and we're going to cover some of them now. We're going to review some of the tooling, some of the methods, and how to apply our tools in certain ways to get the most out of it. But before we get too into the specific tools, I wanted to just cover some of the background information on the tooling to show why some tools are good for titanium over others. And just to give some people a bit of information about the design of tools, I'm going to cover some of the geometry now. So as this slide shows, there's a range of helix angles that you can use for cutting. Now, some tools are better with a lower helix, some tools are better with a higher helix, and this can really affect the rigidity of the tool, the shearing action of the tool, and how fast the chips are evacuated out of the cutting area. So for titanium, you're looking between like high 20s, low 40s for your helix angle. You get a good level of rigidity. You also get that quick evacuation of the chips and the shearing action to cut through the titanium and remove the material you're trying to get. When you talk about rake angles, we can have positive and negative rake angles. Generally, the higher the angle of the rake, the less power is needed to remove the material, because you get that increased shearing action. The lower the angle, the more strength you hold back in that tool. So you've got a bit more brute force to get in there and do some aggressive roughing, slotting, pocketing, etc. that helps get those chips cut, cleared, and evacuated quickly without causing any recutting or any excess heat going back into your chips with material or your tool. So there's a fine balance between what angle you use for what application, and this we'll discuss this further when we get into some of the details of the tools. Number of flutes. So this really depends again on your application and what you're aiming to do. So are you aiming to get material out there quick? Are you aiming to take a large chunk of material out, or are you looking to finish a thin wall, for example? This can lead to all how you go about picking what number of flutes you want for your material. You can also go odd number of flutes or even number of flutes. You can go oddly spaced or even spaced. There's many different types, and how this decision is made again comes back to what you're doing. So the lower flutes you have, the more room you have in there to make a big chip and get those chips out of your cutting area. This is great for slotting, for heavy duty roughing, traditional profiling passes, where all you need to do is get that material out. Surface finish isn't as critical, and you're looking to get close to a semi-finished surface. So you want to go aggressive, you want to get the chips out of there fast, you want to go for a lower flute count. When it comes to lower flute count tools as well, you've also got to consider the harmonics of what you're doing. So if you've got an even number of flutes and they're equally spaced, you've got a potential issue for chatter generation because of always having two flutes coming in and out of cut. So you get that repeating knock-in effect where you've got flutes engaging and coming out of cut that can cause you issues. If you have an odd number of flutes, you avoid that because you've got one chip cutting, one flute cutting, excuse me, one flute engaging, and one flute coming out of cut. So all that harmonics are affected positively because you're distributing that harmonic effect that can get amplified and cause tool failure, chatter, poor accuracy, and tool life. The higher you go with flutes, the faster you can go, but the lighter depth of cut you've got to apply, because there's less room for your chips to get in there and there's less room for your chips to get out. So you can cut, if you go too aggressive with a high flute count tool, you can encounter chip jamming, chip recutting, and that can really affect your tool life and your cutting performance. So there's a balancing act between what you want to do and how you want to do it. There are tools that will do a roughing and finishing operation. We'll cover that shortly. But there are some tools that if all you need to do is get to a rough profile, or you have quite wide tolerances on your components, a lower flute count tool going aggressive may be the way to do it. But again, it comes back to the entire setup. It's not just the tool you've got to focus on. When it comes to the relief of a tool, again, this can be determined by the tool you select, and again, whether you are roughing or finishing. So if a tool has an eccentric relief behind it, behind the flute, you get more meat and strength behind that tool, which lets you cut more aggressively because you've got that extra material that's backing up the face, that's cutting and engaging into the tool. So this gives you extra strength for aggressive roughing and without causing issues to your tool. If you go for a faceted relief, you get a really, really sharp cutting edge. So great for light cuts, really fast. Great for really light finishing and softer materials. The eccentric relief, again, because you've got that extra meat, is great for harder materials. So this comes to, again, as I mentioned, what is the right tool? What are you aiming to do? So are you roughing, are you finishing, or do you want a tool that does both? Are you slotting, pocketing, or profiling? Do you need to plunge? Can you helically ramp? And do you need long reach tools? Have you got a fixture setup or an application where you've got a really deep pocket or a really difficult surface to reach that you just can't get to with a standard length tool? Do you need chip breakers? If you're pocketing and you haven't got sufficient coolant to help evacuate your chips, do you need chip breakers? Rather than doing a 1 inch length of cut and getting a 1 inch length piece of swarf, can you use chip breakers to help cut those cut that swarf down, make it easier to evacuate using coolant or air? Are you using high-speed machining techniques or more traditional methods? So are you just going in there and profiling round? You're not cornering around your component. You're just doing straight 90-degree corners. Again, this all comes back to how you apply your tool and what method you're using. If all you are doing is doing a square profile around a block and you've got really sharp corners, titanium don't like that, and neither does your tool. You know, you're rapidly increasing and altering the direction of force applied to your tool in those corners. If you can put a radius on each of those corners, not only will you increase your tool life by balancing the cutting forces applied, you'll also get a more accurate component, and it'll be way easier on your machine tool as well. Again, how you apply a traditional method or a more advanced method, such as trochoidal milling, depends on a couple of options, such as your machine tool, your CAD/CAM program, and what you're aiming to do. If all you are making is 3 components, you might not need to go to the level of engineering where you're doing trochoidal milling or you're doing really high efficiency programs, because you're just making 3. So you don't need to invest that level of time into your programming and your on machine time. If you're making hundreds or thousands of these components year in, year out, then yes, take the time to understand how you're doing it and how to get the most out of your tool. Trochoidal milling, pocketing, high efficiency machining, they're all great options when titanium machining, because you're looking after your tool, you're looking after the material, and you're looking after the machine tool. So there's multiple ways of determining how you go about selecting a tool. So which tool is the right tool? Now, we've got on this page, there's a number of our tools. I'm not going to go through all of these. Don't worry, this isn't a giant sales pitch on every tool. We've got finishing tools, roughing tools, multi-purpose tools, 2 drills in there, and I'm just going to give a top level introduction to the more common ones and how they're used and what they're best used for. But we'll start with drilling. So we've got the Hypercarb. So this is a twin flute, secondary flute drill. It can drill 3 or 5 times D. It comes with a Dynamite A coating, which gives you excellent heat protection on your carbide. And the double fluting gives you great stability in hole drilling, because you've got that extra flute behind your cutting flute to help stabilize the hole. You've effectively got 4 points of contact over 2. So this allows for excellent rigidity and stability. You also get an increase in circularity and accuracy through a burnishing effect from the secondary flute that helps guide that drill down to the right diameter and the right path. It also allows for coolant to enter down into the drill area to help evacuate those chips. You get the chips out there, you increase your tool life, you increase your accuracy. This tool is available. We've got over 450 different options for this tool. They come in fractional sizes and metric sizes, and it's a great tool for using that can just day in, day out, give you a repeatable hole. The second drill that I want to discuss is the IceCarve. Now, this is a through coolant drill. It's great for the deeper 8 times D holes, or areas where you really want to get the most out of tool life, or you don't have great flood coolant access. So if you're going into you're creating a hole that's inside a pocket and you're using flood coolant through some nozzles that you just can't get positioned right for your drilling up, this is a great opportunity to maximize efficiency through using a through coolant drill. As you're aware, that you drill into your hole, and the coolant is coming straight out in the bottom of the hole, flushing those chips straight out. So you get great tool life with this drill, and it's just great for those applications where you just can't get enough coolant into your cutting hole. So Zcarb HPR, I love this tool. I've used this tool probably more than any other tool that we sell. There's over 800 different options of this tool. It comes in fractional, it comes in metric. You can get it with a square cone, you can get it with a radius. You can get it with a through coolant hole in certain sizes as well, which is phenomenal when pocketing or slotting. It's got a very big core, which gives you great stability, and it's excellent for profiling. So you've got all the right geometry here that gives you great efficiency when rough milling. You've got the 5 flute odd pattern, they're variably pitched, you've got variable rake, and with a Dynamite M or even the Dynamite A coating, you get excellent tool life. I did a project, a development project that we're doing using this tool for trochoidal milling, and it gives you a surface finish that's fantastic at very aggressive rates. In fact, later on, I've got a slide discussing coatings that will show the application of this tool. You can also use this tool for finishing. It's called a high performance rougher, but it does work well as a finisher as well if you're limited to your pockets on your machine. So you've got no worries about just altering your feeds, altering your parameter, your AE, your AP, and you'll get a great surface finish with this tool as well. The Vcub, this is perfect for finishing. I'm sure some of you have come across this tool before. It's got, again, the great geometry, the unequal indexing, the right helix. You can get it in ball nose, square, and it's a very, very useful tool. You can do roughing with it, but you've got to be careful not to go too much radial engagement. And again, just fantastic all-around tool that excels at finishing. The Zcarb, this is a 6 flute end mill, unequal indexing, center cutting, great for trochoidal milling, great for helical interpolation into pockets, take really light radial passes, high AP passes, axial passes, and you can really ramp up your parameters and get in there and get that material out. It's great for pockets because you've got that extra length of cut in there that you won't have with some of the Zcarbs or the Vcubs. You do it completely different programming to how you'd use a Zcarb. So this is really high efficiency. So as I mentioned, high AP, low AE, get your parameters ramped up, and you can profile around a component all day with this tool. It's fantastic. Now I'll come to a 7 flute tool. This is a great all-round tool. I've been working with the sales engineers up and down the East Coast, and they're using this tool on pretty much every material that you can come across, and it works phenomenally well. 7 flutes, it's an open-centered core, it's unequal indexed, it can come in Dynamite M or Dynamite A coating, depending what you're machining. And again, this is great for really high speed, low radial engagement, profiling, trochoidal milling, profiling. It's excellent. As with all of our tools, it comes fractional or metric, so you've got a good range of sizes in what you want to do. And it also comes in a chip breaker option, as you can see in the drill, in the end mill on the right. Apologies. So again, if you're doing a deep pocket or you've got a really high wall, this is great for cutting that swarf into really small, manageable pieces. You aid with chip evacuation. You don't get the swarf clogging up in your machine bed, and you don't get it clogging up on its way out on the conveyor. So it just makes everything really, really manageable. It also comes in a wide range of axial lengths of cut, so up to 4 times D, which is great, especially if you've got a big 3/4 or inch end mill. You've really got a long length of cut in there that you can take advantage of and really work that tool efficiently. It needs to be worked hard, but it works really well in very high speed machining applications where speed is the name of the game. You know, this isn't a tool for slotting, but you want to do fast machining, this is perfect. And this is the last tool I'll cover. This is the Zcarb AP. AP is advanced productivity. We've got 250 different versions of this tool. So we've got long reach applications. You can get it square, corner radius, or ball ends. As I mentioned, with all the other tools, it's fractional or metric. And it's got 3 levels of chatter suppression, this tool. So you've got variable helix, unequal indexing, and variable rake. So you've got 3 methods of chatter suppression in this tool. So you can really work this tool at high speed because there's all this geometry in the background working for your advantage to reduce chatter. A lot of our other tool, the Zcarb, which is just a 4 flute, has 2 levels of chatter suppression. If you're using a Zcarb, you're still finding you're getting chatter in certain areas, an AP might be a good option to just swap out and try, because you've got that extra level of suppression in there that helps you increase tool life. And that's it for the tools. So we'll come to talking about coatings now. I've had several discussions in the past with a couple of different customers as to do coatings make a difference in titanium? And yes, they do. It's clear and fast, and they sincerely offer a great improvement in tool life when applied to the right tool. So Kyocera SGS offers a wide range of coatings, but the 3 I just wanted to cover on now is our Dynamite A, our Dynamite X, and our Dynamite M. So you can, in any application, use these coatings, and you'll find that one excels and the other 2 work well, but you'll always find that one that works great. In the tool development project that I did, we used Dynamite M exclusively, and we got excellent tool life. We never had any issues with built-up edge, adhesion. We got great thermal protection of the tool to reduce chipping. It was fantastic. That's not saying that A and X are bad. It's just how you apply them into your application, and working with the applications engineers from Kyocera SGS or the sales engineers from SGS, and also which tool you use will be able to steer you into the right path of which coating is best for your application. And as I mentioned, the coated versus uncoated discussion, this is a project I was working on. You'll have to excuse the image on the right. I had to make it brighter to try and highlight some of the damage and the differences between the tool. So this is our Zcarb HPR. It's a 12 mil Dynamite M coated, and this was a trochoidal milling operation. So we were running at 85 meters a minute, just under 2,300 RPM, 80 millimeters feet per tooth. This was a 12 mil deep slot, 15 mil wide, trochoidal milling with a 16% radial step over. And this was just to highlight how much more improvement you can get from swapping out an uncoated tool to a coated tool. And sometimes you think, oh, well, a coated tool is going to cost more. Well, it does, but it doesn't cost that much more. The table at the bottom shows that a coated tool it used here was $137.13. The uncoated was $130.27. So $6.86. 5% difference. Now, when you look at the number of slots produced and the runtime, this is where things get interesting. The coated tool managed to complete 42 slots. Now, when we were doing this trial, we were only aiming to complete 30, and it did it, and the tool still looked fantastic. You can see the tool on the left is the Dynamite M coated tool, and you can see that those cutting edges, there is a very small amount of built up edge, and there is some coating wear within the flute. But when you compare it against the tool on the right that only did 23 slots before the wear was excessive, you can see that there's a lot of chipping on there, there's a lot of material built up on the edge, and that tool's done for. So you could run it until it fails, but nobody wants to do that because titanium is expensive and your components are even more expensive. just by adding the coating, we got 46% more tool life in this application. And this is aggressive parameters, trochoidal milling, Ti6Al4V, and it's a great indicator to show what you can achieve by applying the right tool to the issue. There are some times where you don't want to use a coated tool, however. Some aerospace companies don't use coated tools for finishing in titanium because of microcrack. But for the majority of people, this isn't an issue. But there are certain applications where, no, you can't use a coated tool. But if you're roughing, always aim to hit it with a coated tool. You'll get better tool life. You'll get better surface finish because your tool is being protected by that coating. So you get less chipping, less damage, and you get better chip evacuation because of the slickness, for want of a better word, of the coating. Coolant. So coolant is critical when it comes to machining titanium. You need to get plenty of coolant in there. It needs to be the right type of coolant. It needs to be applied as close to the cutting edge as possible, as much pressure as possible. But if all you've got is flood, that will work as well, and we'll cover that shortly. So it's the heat built up that causes the most damage to the tool. You get that heat in there, it burns, it wears through the coating, it goes into your carbide substrate, and failure happens inevitably. Coolant doesn't just protect your tool or your component from excessive heat. It helps lubricate the cutting edge against the material, so you get a smoother cut. It helps in chip evacuation. As I mentioned with the IceCarve earlier, you've got that through tool coolant that's getting in there, forcing them chips up and out through the hole, through the flutes. You can use coolant as efficiently as possible to get those chips out of the way quickly. You prevent recutting of chips, which damages your tool, causes excess wear, and can damage your component. Now, coolant can be a tricky thing to manage, but if you work with your coolant supplier, keep it clean, keep the fungus from growing in it, and keep it at the right concentration, it will make a massive difference to your tool life. If you can use high pressure coolant, brilliant. If you want to use an open collet to get that coolant out and down around your tool, that's brilliant. If you just want to use nozzles and aim that coolant as close to the cutting area as you can, as in the image on the slide, that's as good. You know, you've got to get that coolant in there, you've got to get it pushing them chips out, and you've got to get it pulling that heat out of the cutting zone. However, if you don't want to use an open collet, or you don't have great access to your cutting area because of fixturing, or the area you're machining is deep inside a pocket, Case SGS offers Jetstream slots. Now, this is a coolant application system where you can use a sealed collet on your tool, and as long as you've got through tool coolant spindle capability, you can use these tools to get coolant right at the cutting edge. So as you can see in the image on the right, the slots are timed with the flute so that you get a direct application of coolant down the side of the tool into the flutes and straight at that cutting area. It's excellent at giving you precise application. So just like using a sealed collet, it's coming round the tool straight towards the center. It's not coming through the tool like it would in a Zcarb HPR, where you've got your center through coolant hole or your IceCarve drill, but it's getting that coolant in there, and it's getting that coolant in there consistently because it's right against your cutting flutes, right against your tool, right against your component, and it's giving you as much evacuation and as much cooling capability, as much lubricity as it can by getting it right at the cutting edge. Again, as I mentioned, by getting those chips out of the way and controlling that heat, you will improve your tool life, because you've got to get a stable cutting area to give best longevity to your tool. So we talked about the tools, we've talked about the geometry, we've talked about coolant. Now let's talk about how to get the most out of your tools through intelligent programming. Now, you can program very traditional. You can do straight engages onto corners. You can engage into pockets, you know. But the more intelligence you build into your programs, the better you will be all round. You'll get improved tool life. You'll get improved swath control. You'll get improved geometry of your components. You'll reduce tool failures. You'll increase productivity. If you ramp engage straight into a corner or into an arc, like shown in the image of the left, that's a massive amount of shock being hit onto that tool in one direction very quickly. You're getting a lot of wraparound on that tool, and that's a large amount of force being instantly applied to your cutter. You'll get chatter, you'll get noise, you'll get vibration, and you could, if before you've even started machining anything, damage your tool. A more intelligent way to do it is to walk into the cut. So don't just directly engage, arc into it. If you are cutting a rectangular block of titanium, don't just feed straight into it from one corner. Arc round it, build into cut. Gradually increase that force applied to your tool until you've got it fully engaged to your depth of cut that you want. Your tool will thank you for it. Your component will thank you for it, and your machine tool will as well. You'll get that gradual increase. Your tool will bed into it, and you'll start cutting, and everything will be better. And all for a simple engage, you know? Like this isn't mind bending. This isn't critical cutting edge technology. This is just how to go about getting the most out of your tool and cutting the titanium as nicely as possible to maximize your productivity. If you snap a tool engaging straight into a component, you've got downtime. You've got to swap the tool out. You've got to check that the component's okay. You've got to check that the holder's okay. You've got to drop the tool. You've got to pull the holder out. You've got to go through all that rigmarole of getting back set up, ready to go. All for potentially just using a bit of background knowledge, a bit of thinking about how you program. If you are forced to go straight into cut, as per the image on the left, just drop your feed. Just drop your feed 50%. You'll ease the tool into cut a bit better. It'll give you time to just settle in before you set off profiling around your component. As soon as you're in and you're at your required radial cut, turn that feed back up and away you go. But it's still not as good as arcing in and arcing out of your cut. That sudden increase of cutting force or sudden release of cutting force can cause damage to your tools. So this applies when cutting corners as well, and the size of tool you're using. If you are cutting a 1/2 inch radius, don't use a 1/2 inch tool. Step down to a smaller diameter. As per the image on the right, if you have an 1/2 inch tool, cut bigger than the corner you require. Leave the material in there for a later operation, or use a smaller tool but go high efficiency machining. Sure, you might go from using a 1/2 inch or a 3/4 inch end mill to do some aggressive roughing. Maybe step that down to a 1/4 inch or a 1/2 inch and go light and fast. Peel away that corner, keep your radial engagement to a sensible amount. You'll keep your cutting forces stable. You won't wrap around in that corner and increase that cutting area contact angle massively, which can cause it will cause chatter. It may damage your tool. It may even cause your tool to fail. If the swath gets jammed in there, you cut and you're out of the game. So use your programming capabilities in CAM to your advantage. As I mentioned earlier, if you're profiling round a boss, don't use square cut, don't use 90-degree corners. Ramp round. It'll keep that cutting force consistent and gentle for your tool. It'll improve your productivity no end at all. So a lot of you probably know about high efficiency machining, trochoidal milling, getting the most out of your tool. This is moving away from traditional machining methods. So this is taking advantage of your CAM software that allows for advanced machining capability. This is all about using the most efficient milling methods possible. Yes, you can slot and then you can profile, but it's heavy on your machine tool, it's heavy on your tool. It can cause chatter. If the application isn't right, if you haven't got a really stable setup, for example, slotting can cause you no end of problems. And yes, you can drop your axial depth of cut and take multiple passes. But as the old saying goes, time is money. Why try and aggressively do something that can cause damage long-term to your machine tool, your component, and the tool, when you could use some intelligent machining methods such as a trochoidal path to get in there and go really fast, really light, really easy on your tool, and just cut all that material out without causing too much stress, strain, or problems to your machine. This method of trochoidal milling, using constant cutter engagement, you get lower heat because you're coming in and out of cut, but it's gently coming in and out of cut. It builds into cut, you reach your maximum radial cut, and then you're already coming back out. Yes, you may need to go down and do a finish pass after, but if we're talking a quarter, 50 microns depth of cut, then you can just simply go in and out of your slot really fast, really light, and get an excellent surface finish. You've got a great surface finish already for a rough condition because of the trochoidal milling method, the high efficiency method, where you're keeping your cutting tool engaged all the time, keeping that force consistent, giving an intelligent bed for your programming to be efficient. Depending on the application, sometimes you will find that a trochoidal milling or a high efficiency pass is slightly longer than a traditional straight pass, rough in, heavy duty milling. But what you've got to consider is if trochoidal milling takes you 10 seconds longer, 20 seconds longer, but you get 3 times the tool life, where's that balancing act? Are you making 1? Are you making 10? Are you making 1,000? If you're making 1,000, then you need to look into your cost analysis for runtime, tool cost, machine tool time, all the little costs that build up. Is 10 seconds going to become a deal breaker? If yes, well, then what's the cost of the tool between a high efficiency milling tool such as a T-carb versus a more aggressive tool that you could use, such as a Zcarb HPR, and just slot? You've got multiple options. So never just think, well, SGS said you've got to use a high efficiency milling method. Sometimes you can just do a full slot and you'll get away with it, but you've got to tailor each thing to your solution. Each application is different. What works for one company won't be correct for another company. So it all depends on the job, the machine tool, the fixturing, the coolant, and the cost of the component at the end of it. When it comes to using these high efficiency milling programs, or you are profiling around a machine tool, your engagement angle of your component can change. So if you are machining around a profile, for example, and you go into a corner, your engagement angle increases because you get more wraparound. As you come to the outside of a corner, if you're profiling around a boss, your engagement angle decreases. So what you're programmed is your feet per tooth is not actually what you get. Inch per tooth is not what you're getting, because your chips are varying in size. When you're going along a straight path, you're getting the exact parameters you programmed at. But when you go around a boss, you're cutting less. So your tool can start rubbing instead of cutting. If you're not cutting and you're just rubbing, then your heat is going to massively increase. Your tool life's going to fail and your part quality is going to suffer for it. So what you can apply is what we call chip thinning. Can you utilize a higher feed rate and improve your production time by taking advantage of varying your cutting engagement? If you go into a corner, you got to slow down. You got to maintain that that feed rate, because you've got more radial engagement, you've got more force applied to your tool, and that's going to cause issues with tool life. If you drop your feed there, there's no reason why when you come up to machine around a boss at the end, you can't increase your feed rate, get that time back, keep that inch per tooth at the same level, and your CAD programs, your CAM programs will assist you in this. You can set it to do this. You can set alternative feed rates for your corners, whether they're internal corners or external corners. If you're doing the programming, you've got the program on the machine already, you don't want to go back into your CAD CAM software. On the Kyocera SGS website, we have a calculator that works it out for you. So I've just done a quick example here. It's based on a 1/2 inch 5 flute diameter end mill, taking an 0.5 radial width of cut at 250 feet per minute and 23 inch, just under 24 inch per minute. If you use the chip thinning calculator, which is just at the bottom, if you are varying your chip thickness to less than 50% of your cutting diameter, you're actually not getting your inches per minute that you're programmed to. Right? So therefore you can increase that inch per minute, and the calculator here shows that you can optimize that to 39.8 inches per minute, up from 23.88. That's a significant saving. That's if you are looking to get the extreme amount of productivity out of a repeat component, look at your chip thinning, because not only will you get better tool life for it, you'll save time as well, and you'll get a better component out of it as well. Now, I can't in this presentation give you a set of parameters and say this will work because this is exactly what our book says. Please refer to our book, refer to our Tool Wizard, which I'll come to later. Talk to our sales guys, talk to the application guys. Depending on what you're doing, how you set up, what machine tool you're using will affect how you set your parameters. And the bold point on the top right, proper speeds and feeds take experience and experimentation to determine. Cannot agree more with that statement. Just because you run at one set of parameters doesn't mean you can go 10, 20, 30% faster. Some applications you're going to have to drop that down, but you've just got to get in there, examine your application, and determine what works in that application. I'm just going to go through this quickly. I realize I'm getting close to time, and I have several slides left, and we want questions at the end. So what happens when you encounter tool failures? You've got possible causes and possible solutions. Now, it could be that you're getting creating on the ends of your tool. This could be any number of issues causing that. But at the same time, there's other solutions and there's probable other issues that you will encounter where you can say, okay, well, the speed's too high and the feed rate's too low. That matches with the other issue that we're having with built-up head, for example. So solutions, there's more than one way to fix this issue. You can alter your parameters. You can improve your coolant access. You can swap out to a bigger holder. You can reduce your stick out. There are always ways to improve and mitigate issues. So just for example, as I mentioned in the earlier case study example for coatings, you got chipping on your cutting edges. Okay, well, some of your causes could be, you could have run out. Well, yeah, like put a clock on your tool and make sure it's running within the holder's limit. You could have an excessive feed rate. It could be as simple as this tool doesn't have a coating on it. Try a coating, try a different tool. Talk to the applications guys and the sales guys. If we don't know the exact answer, I guarantee you will be able to find somebody who does have the answer, who's come across this issue before and who knows how to find a solution that will work. There are many different options when it comes to fixing things and diagnosing these issues. The built-up edge can be a big issue in titanium. That again can come down to running too slow. It can be to overusing your tool. It can be to inefficient coolant. There are many ways to fix that issue of built-up edge. You know, so if you have an issue, just take a step back, look at the overall application. Have I got coolant in the right place? How long has this tool been running for? Has it got a coating? What are my parameters? What works on another machine that doesn't work on this machine? Is it the machine? Is it the fixturing? There are ways to just diagnose each of these issues and find them a sensible resolution that doesn't cost you downtime. If it's a case of you're running too slow, you can adjust your feed and speed 10%, 20% on your machine controller, depending which machine tool you're using. So there are ways to just deal with these issues. The final issue I'll come across is catastrophic failure. And that on the right is one of mine. I enjoy using a tool and and in this application, we were trying to get the most out of the tool. This is actually one of the tools that failed in the case study when we were discussing earlier. So if you're running your tools to this length and you're getting this issue, it can be caused by several issues. You might have just run it for too many slots. You might have got too aggressive parameters. You might have your chips not evacuating correctly because you're not getting enough coolant in there to get them evacuated, and that can cause them to jam, and then you just twist your tool off and you've potentially scrapped a $10,000 to $250,000 component, and nobody is going to be happy about that. Make sure that when you are running these tools, you apply logic to them, you gain from your experience of running them and say, right, this tool has run for an hour, full slotting. That's it, it's done. It's run for half an hour doing X, it's done. Back it off, put a factor of safety in there. If you can give us a worn tool that's not badly damaged, we can regrind it for you. A reground tool is 98% a brand new tool. It's just a bit shorter. We'll recoat it for you, send it back out to you, and it's something that we can do with a lot of our tools. A really efficient way of getting the most out of a tool. Just apply logic. Just if you are cutting and the cutting conditions change, it feels different holding the glass on the machine tool, you know you've got an issue. Take a step back, have a look at the overall thing, have a look at the overall application, and determine what you can do to make a positive effect before it becomes an issue. What you can also do is refer to our website. On our website, sgstool.com, we have case studies. So you go to resources, you drop down to case studies, and you can find case studies by material, by industry, or by tool series. For the titaniums, we currently have 7 all available using different tools, using different applications with different results. These are real world applications that where we have worked with a customer who has a current engineering issue. We have come in, we have worked with them. We have just given them the guidance to say, you're currently doing this. Let's try this. Let's increase this. Let's put a coating on this tool. Let's increase the depth of cut axially, but drop it radially. These are real world case studies. This library is being built all the time, and there is plenty of research out there that we can help you with. So in summary, you got to know which material you're cutting. Your titaniums, there's different grades. Now you can get away with using generic titanium parameters for a lot of these, but some are different. You know, if you go from cutting Ti 6AL4V to cutting Ti 10AL, 2FE, 3AL, you've got to use different parameters. It's a different material. It's got different properties. It's more aggressive on your tool. You've got to tailor your solution. Know your limitations. If you're running on a small machine tool that's got a small holder, that's got low pressure coolant and a limited spindle capability, you can't be pushing it at 120%. You know, you've got to just set up your system for its limitations. If you've got a giant DMG or another big 5-axis, big head, high pressure coolant machine, for example, yeah, you can go more aggressive. You've got that stability in there. Talk to us, talk to your sales rep, talk to the applications guys. We're here to help you. You know, like, we want to help you. We want you to succeed. We want our tools to impress. So if you want to talk about an application, my contact details will be given at the end of this presentation. If you're on the East Coast, reach out to me. I'm the applications guy for the East Coast. If you're on the West Coast, reach out to Chris Dixon. He'll help you with that application. If you're in the middle, reach out to Scott Suckup. He'll help you. And between the three of us, plus our sales team and our R&D guys, we'll be able to find a solution for you. The last thing I want to cover is the Tool Wizard. So SGS, Kyocera SGS has a Tool Wizard. This is on our website. You can see the link at the top of the page. And this will help you find tools and parameters for a massive, massive range of materials. There's a good range of titaniums in there. And what you can do is you can tell the Tool Wizard what you are trying to accomplish and what parameters you are capable of. Max RPM, for example. You can select your material, you can select the type of depth of cut you need, and it will recommend you a tool. Do you want a high performance tool? Do you want a general purpose tool? It will give you that option. And it'll give you this calculation page, which I've had to cut down into sections on this slide, and it will give you everything you need to get you up and running. This doesn't mean that you can't adjust these parameters. If you set it going and you get in chatter because your fixturing is not perfect, drop the parameters 10%. Or increase the parameters 10%. Sometimes just moving past that frequency of vibration will get you going again. So use this as a guide. It will give you a great indication of the tool you need. It'll give you a great indication of the parameters you need to use. And that's me. I hope you enjoyed this webinar. If you have any questions, I know we're a bit short on time now, but if you have any questions, I'd like to open it up to questions. No one?
Hello, this is Tan from Singapore. Thank you, Andy, for the presentation. I'd like to ask, in one of your slides, which shows the chip thinning calculator,
Yes, sir.
Is that available? I mean, for us to download or to calculate?
Yes, if you just go to our website, let me just go to our website and you can go to resources and calculator. And it will be there to help you straight away. We have a couple of different ones. We have fractional, we have metric, we have end mills, and we have drilling capabilities in there as well.
So this calculator actually only calculates the optimal chip size, and is slightly different from the Tool Wizard, which actually gives you the cutting parameters.
Yes, sir. So you can put in some parameters in there to give you to get you started on what. So if you can put in your RPM and you know your end mill diameter, it'll calculate your surface feet per minute. You can put in your inches per tooth, and it'll give you your inches per minute. And it's just helpful to get all the parameters in front of you of what you may need to use.
All right, thank you. The other question is your slide for the comparison between a coated and uncoated milling. I think that is for the HPR.
Yes, sir.
Yes. I'm just curious about the cutting parameters. The cutting speed 85.5 meters per minute. Is that considered high in terms of titanium machining?
It's pretty aggressive. You can definitely go higher. There's no, again, it all comes back down to the application and the setup you have. If you have a really rigid machine and a really well fixtured on a big component with thick walls, and you get the right tool in there, the right programming, you can definitely go faster for sure.
Okay, because I think one of the biggest concern about titanium machining is the heat generation.
Yeah.
Which may so-called harden the material itself, right?
Yeah, and again, it all comes down to the application. If you've got excellent coolant access, you can really ramp things up. If you're struggling to get coolant access, your heat's going to become an issue. Your parameters are going to have to change. You may not be able to go as aggressive radially or axially, and it's all a balancing act.
All right, thank you. That's all for me. Thank you.
Thank you.
Anyone else have any questions for Andy? All right. Well, if no one has any questions, we're going to thank you, Andy, for your for the presentation. We all appreciate how much time was put into this, and we appreciate at KSPT. We appreciate everyone's time. Thank you for joining, and we hope to see you at our next event.